The land does not reveal itself easily. At altitude, the Australian interior appears uniform, an expanse of muted browns and grays stretching beyond the limits of visibility. There are no defining edges, no clear elevation changes, only subtle gradients of terrain that shift almost imperceptibly beneath the aircraft. Distance becomes deceptive. Depth becomes uncertain. Below, the ground holds its silence. It is late evening. The last light of day has already thinned into a narrow band along the horizon. Above it, a layer of high cloud disperses what remains of the sun, flattening contrast and removing shadows. The sky and earth begin to merge into a single, indistinct plane. Inside the cockpit, the environment is controlled. Instruments glow steadily. Altitude, heading, vertical speed. Each reading precise. Each input deliberate. The aircraft continues on a stable descent profile, guided not by what can be seen outside, but by what is interpreted within. There is no visual reference to confirm position. This is not unusual. Across much of Australia, particularly beyond the coastal corridors, aviation has long depended on procedural navigation. In earlier decades, radar coverage was limited. Ground-based navigation aids were sparse. Pilots operated within defined procedures, timing, headings, altitude steps, constructing an invisible path through controlled airspace. It was a system built on discipline and on trust. The aircraft continues its approach. Outside, the terrain rises gradually, though it is not apparent from the cockpit. There are no city lights to define the horizon, no shoreline to establish orientation. Only darkness, deepening by the minute. A slight correction is made, a minor adjustment in descent rate. Everything appears normal. Yet within this environment, where visual cues are absent and reliance on instrumentation is absolute, small deviations carry weight. A misinterpretation, a delayed recognition, a procedural assumption carried just slightly too far. There is no immediate warning, no abrupt failure, only a narrowing margin. Australia's aviation landscape has always imposed this kind of discipline. Vast distances between cities, remote airstrips carved into isolated terrain, weather systems that can shift without warning, particularly along coastal approaches where fog forms rapidly and visibility collapses within minutes. In these conditions, safety has never depended on a single barrier. It has depended on layers, procedures, training, technology, oversight, and when those layers aligned imperfectly, when one failed to compensate for another, the consequences were not always immediate, but they were often irreversible. The aircraft ascends further. The instruments continue to indicate stability. Altitude unwinds steadily. The glide path is maintained, at least within the limits of available data. There is no sense of urgency, no indication of conflict. But below, unseen, the terrain continues to rise. This is the nature of controlled flight into terrain. Not a loss of control, not a mechanical failure, but a functioning aircraft, under command, descending into an environment it does not fully perceive. Across Australia's aviation history, this pattern would emerge more than once, not always in the same form, not always under the same conditions, but with familiar characteristics, limited visibility, incomplete situational awareness, and systems that, at the time, did not yet provide sufficient warning. Each event, when it occurred, appeared isolated, an incident explained by circumstance. Aviation, however, does not treat such events in isolation. Over time, patterns form. Investigations begin to align. Findings begin to overlap. What once seemed singular begins to reveal underlying structure, gaps in procedure, limitations in technology, assumptions that no longer hold under increasing operational complexity. The aircraft continues its descent. Inside the cockpit, there is still no indication of immediate danger. The crew operates within expected parameters. The environment remains quiet, almost static. Then, within seconds, too late for correction, the margin disappears. The outcome is final. No dramatics, no prolonged sequence. Only the sudden intersection of aircraft and terrain. Silence follows. In the aftermath, attention shifts, not to the moment itself, but to everything that allowed it to occur. Because in aviation, the point of impact is never the beginning of the story. It is the end of a sequence that, when examined closely, reveals not a single failure, but a chain. Across Australia, these chains would be studied repeatedly. From remote outback approaches to coastal descents under deteriorating weather, each investigation contributed to a growing understanding that safety could not rely solely on human precision or procedural compliance. It required reinforcement, redundancy, systems capable of detecting what the human eye could not, warnings that would intervene before the margin disappeared. What began as isolated accidents gradually reshaped an entire aviation system. But those changes came later. At this point in time, the environment remains unforgiving, the infrastructure incomplete, and the margin narrow. Aviation in Australia did not develop under ordinary conditions. From the beginning, it was shaped by distance. Cities were separated not by hundreds, but by thousands of kilometers. Between them lay terrain that was often uninhabited, arid interior plains, rugged mountain ranges, and long stretches of coastline where weather could shift without warning. Infrastructure, when it existed at all, was sparse. Early air routes crossed regions where alternate landing sites were limited, and emergency support was often hours away. Flight, in this environment, was not simply transportation. It was necessity. In the early decades of Australian aviation, aircraft connected communities that had no practical alternatives. Mail routes, medical evacuations, and passenger services operated across vast distances with limited support systems. Navigation relied heavily on visual references, rivers, rail lines, coastlines, and when those references disappeared, crews turned to dead reckoning in basic radio navigation aids. Accuracy depended on estimation. Wind drift, timing, and compass heading were calculated continuously. Small errors could compound over distance, particularly when visibility deteriorated. In many cases, there was no immediate way to verify position with certainty. This was not a failure of design. It was a limitation of the era. As aviation expanded through the mid-20th century, Australia began to introduce more structured systems. Ground-based navigation aids, non-directional beacons, and later VOR stations provided fixed reference points. Airways were established, linking major cities through defined corridors. Procedures were standardized to ensure separation and predictability. But coverage remained uneven. Outside the primary routes, large areas of the continent still operated with minimal navigational support. Aircraft entering these regions relied on procedural control, position reports transmitted at designated intervals, altitude assignments based on timing rather than continuous surveillance. Radar, where it existed, was concentrated around major urban centers. Beyond those boundaries, air traffic control functioned without direct visibility of the aircraft it was responsible for managing. This required precision, and it required trust in the system's assumptions. By the late 1950s and into the 1960s, the introduction of turbine-powered aircraft increased both speed and altitude capability. Flights that once took hours were shortened significantly. Operational ceilings rose, and with them, exposure to new environmental variables, jet streams, high-altitude weather systems, and more complex descent profiles into varied terrain. The margin for error did not disappear. It narrowed. At higher speeds, deviations developed more quickly. A descent initiated slightly early, or maintained slightly longer than intended, could place an aircraft outside its safe altitude envelope before corrective action could be taken. Without continuous terrain awareness systems, crews depended on charts, procedures, and altitude discipline to remain clear of obstacles. In regions where terrain rose gradually, without sharp peaks or obvious visual warning, this dependence became critical. Australia's geography contains many such areas. The Eastern Highlands, for example, do not present as abrupt mountains when viewed from altitude. Instead, they rise steadily over long distances, in reduced visibility. Particularly at night, this terrain can remain indistinct until proximity is already too close. Weather further complicated this environment. Coastal fog systems, especially along the southeastern and southwestern regions, could form rapidly and reduce visibility to near zero within minutes. Inland, temperature gradients created atmospheric distortion, flattening visual contrast and obscuring depth perception. Storm systems, while often isolated, could develop with limited forecasting precision in earlier decades. Pilots operating within these conditions relied heavily on procedural approaches, step-down descents, altitude fixes, timing sequences, all designed to guide the aircraft safely to landing without requiring continuous visual reference. These procedures were robust when followed precisely, but they assumed accuracy in both execution and situational awareness. If either degraded, even slightly, the system offered limited redundancy. At the same time, Australia's aviation industry was expanding. Carriers such as Qantas and Trans-Australia Airlines began operating more frequent services, connecting not only major cities but also regional centers. Traffic density increased. Scheduling became more complex. Aircraft utilization intensified. With growth came pressure, not necessarily in the form of urgency, but in expectation. Flights would be conducted reliably, consistently, and within increasingly structured operational frameworks. Crews were trained to high standards, but training itself evolved over time, reflecting both technological advancement and lessons learned from incidents. In earlier periods, crew resource management, the structured use of all available human and technical resources, was not yet formalized. Decision-making often rested heavily on the captain, with less emphasis on collaborative verification or challenge. This was consistent with global aviation practices at the time, but it introduced vulnerability, particularly in environments where information was incomplete. As the decades progressed, regulatory oversight in Australia adapted gradually. Authorities introduced updated procedures, improved navigation infrastructure, and more rigorous training requirements. However, these changes were often reactive rather than proactive. They followed incidents. They responded to identified gaps. And in doing so, they formed a pattern, one that will become increasingly clear as investigations accumulated. Each event added detail, a misjudged descent profile and low visibility, a navigation error compounded by insufficient cross-checking, a system that functioned as designed, but lacked the capacity to compensate for human limitation under specific conditions. Individually, these were anomalies. Collectively, they pointed to systemic exposure. By the late 20th century, aviation globally had begun shifting toward a more integrated safety philosophy, one that recognized that accidents rarely result from a single failure. Instead, they emerged from aligned weaknesses across multiple layers. Australia was no exception, but its environment ensured that when those layers failed, the consequences were often immediate and unforgiving. The need for change did not arise from theory. It emerged from experience. And that experience would soon be defined by a series of events that forced the system to confront its limitations, not in isolation, but as part of a broader structure that required reinforcement. Aviation safety does not fail in a single place. It degrades across layers, each one designed to compensate for the others. When those layers align imperfectly, the system remains functional, but its resilience is reduced. In Australia, this interaction between aircraft capability, human performance, environmental exposure, and systemic design defined the conditions under which accidents occurred. Understanding that interaction requires separation, not to isolate responsibility, but to examine structure. Aircraft. The aircraft operating across Australia's domestic and regional networks evolved rapidly over the decades. Early piston engine transports gave way to turboprops, and eventually to jet aircraft capable of higher speeds and altitudes. With each transition, capability increased. So did complexity. Navigation systems, in earlier aircraft, were limited to radio-based aids and basic instrumentation. Position awareness was constructed from intermittent signals, non-directional beacons, VOR radials, and distance measuring equipment when available. These systems were reliable within their limits, but they did not provide continuous positional certainty. There was no onboard terrain awareness, no automated system to compare altitude against the ground below. This absence was not unusual for the period. It reflected the global state of aviation technology. However, in an environment like Australia, where terrain could rise gradually and invisibly, this limitation carried specific consequences. Even as aircraft became more advanced, early generations of jetliners still relied on procedural separation from terrain. Safe altitudes were calculated and published. Crews were expected to adhere precisely to those constraints. The aircraft itself did not intervene. It executed commands. Autopilot systems, where installed, provided stability and workload reduction, but they also introduced a subtle dependency. When engaged, they removed the tactile feedback of manual flight. Deviations, unless monitored actively, could persist longer before recognition. Later developments, such as ground proximity warning systems, GPWS, would change this dynamic significantly. But for a substantial period, many aircraft operated without such safeguards. The machine, in these cases, was exact, but not protective. Crew. Flight crews operated within a framework of training, experience, and procedural expectation. In Australia, as elsewhere, pilots were trained to maintain strict adherence to altitude, navigation, and approach procedures. Discipline was central. Accuracy was assumed, but training itself evolved over time. In earlier decades, cockpit dynamics were hierarchical. The captain held primary authority, and while first officers contributed, structured challenge and cross-verification were less formalized than in modern operations. This did not imply negligence. It reflected standard practice. However, in situations where ambiguity developed, uncertain position, unexpected weather, or incomplete data, the absence of formalized crew resource management could reduce the effectiveness of error detection. Fatigue also played a role. Australia's geography required long sectors, often across featureless terrain with minimal visual stimulation. Monotony, particularly during cruise or night operations, could subtly degrade vigilance. Attention, while never absent, could narrow. In descent phases, where workload increased, any lapse in earlier situational awareness could carry forward. Recovery depended on timely recognition, and recognition depended on active monitoring. Experience varied across operations. Major carriers like Qantas maintained structured training programs and operational oversight. Regional and smaller operators, while compliant with regulations, often worked with fewer resources and less technological support. The difference was not always visible in routine operations. It became apparent under stress. Environment. Australia's environment does not present uniform challenges. It presents varied ones, often within a single flight. The interior is defined by scale. Vast, sparsely populated, with minimal lighting and few visual references. At night, the distinction between ground and sky can disappear entirely. Without a visible horizon, spatial orientation relies exclusively on instruments. Along the coast, conditions shift. Fog banks can develop rapidly, particularly in the early morning and late evening. These formations reduce visibility to near zero, often without gradual transition. An approach that begins in marginal visual conditions can deteriorate into full instrument flight within minutes. Terrain, in many regions, does not announce itself clearly. The eastern highlands rise progressively. From altitude, they appear as gentle gradients rather than defined peaks. In low visibility, this creates a hazard. Aircraft descending on a stable profile may be unaware that the ground is rising to meet them. Weather systems, while generally predictable on a macro scale, can produce localized effects that were historically difficult to forecast with precision. Thunderstorms, turbulence, and wind shear introduce additional variables into already constrained operations. In this environment, visual confirmation could not be relied upon consistently, and when it disappeared, the system shifted entirely to procedural and instrument-based control. Systems. Beyond the aircraft and crew, aviation safety depends on external systems: air traffic control, navigation infrastructure, regulatory oversight. In Australia, these systems developed unevenly, shaped by geography and demand. Radar coverage, for much of the 20th century, was concentrated around major cities, such as Sydney and Melbourne. Outside these areas, controllers relied on procedural separation. Aircraft reported positions at designated waypoints. Altitudes and timings were assigned based on expected progress. There was no continuous tracking. This system functioned effectively when all variables remained stable, but it offered limited capacity to detect deviations in real time. If an aircraft descended below its assigned altitude or drifted off course, recognition depended on the crew's own reporting. Communication infrastructure also introduced delays. In remote regions, radio coverage could be intermittent. Position reports might be delayed or relayed through intermediate stations. This created gaps, not necessarily failures, but intervals where the system operated without full awareness. Regulatory oversight, managed by bodies such as the Civil Aviation Authority and its successors, established standards of operation, training, and equipment. These standards evolved over time, often in response to identified deficiencies. Investigations played a central role in this evolution. Each incident was examined in detail, not only to determine cause, but to identify systemic vulnerabilities. Recommendations were issued. Some were implemented immediately. Others required broader industry alignment. The process was deliberate, but it was not instantaneous. As a result, there were periods where known limitations remained unaddressed, simply because the mechanisms for change required time. Convergence. Individually, none of these elements guaranteed failure. Aircraft were reliable within their design limits. Crews were trained and experienced. Environmental conditions, while challenging, were understood. Systems, though incomplete, were functional. The pattern did not emerge all at once. It formed gradually, through events separated by years, by geography, and by circumstance. Each accident carried its own narrative, its own sequence of decisions and conditions. But when examined collectively, they revealed a structure that could no longer be dismissed as isolated. In Australia, several accidents would come to define that turning point, not because they were identical, but because they exposed the same vulnerabilities from different angles. Case 1. Descent into invisible terrain. The aircraft was operating a scheduled passenger service. The route was routine. The approach familiar. Weather conditions, while not ideal, were within operational limits. Visibility was reduced, but not absent. Cloud layers obscured high terrain, and the remaining light of day offered only minimal contrast. The descent began as planned. Altitude restrictions were published. Step-down fixes defined the profile. The crew followed the procedure, adjusting rate of descent, configuring the aircraft incrementally. Instruments indicated compliance. There was no indication of deviation beyond acceptable tolerance. Outside, the terrain rose. Gradually, without visual definition. This was not mountainous terrain in the conventional sense. There were no sharp peaks, no distinct ridgelines visible from distance. Instead, elevation increased steadily beneath the flight path, an incline that, in clear conditions, would be apparent, but under reduced visibility, it remained indistinct. The aircraft continued descending. At a point where altitude should have been stabilized, the descent persisted slightly longer than required. The deviation was small, measured not in thousands of feet, but in hundreds. Within the cockpit, this did not immediately present as critical. There was no automated terrain warning, no auditory alert to interrupt the sequence. Recognition came late. When visual cues finally emerged, they did so without clarity. Only a dark mess forming ahead, insufficient to interpret distance or rate of closure. By the time the terrain was positively identified, the margin had already been consumed. Corrective action was initiated. But altitude, once lost at that stage of approach, could not be recovered in time. The aircraft remained under control. The trajectory did not change. It intersected the rising ground. The investigation would later classify the event as controlled flight into terrain, a functioning aircraft descending below safe altitude without awareness of proximity to the ground. There was no mechanical failure, no single decisive error, only a continuation of descent beyond a critical point, in an environment that offered no warning. Case 2. Weather, assumption, and delay. The second event occurred under different conditions. Night had already fallen. The aircraft approached a coastal airport where fog had been reported intermittently throughout the evening. Visibility fluctuated, at times sufficient for visual reference, at others reduced to instrument-only conditions. Forecasting indicated variability, but not severity. The crew initiated the approach with expectation of visual acquisition near minimum descent altitude. This expectation was not unreasonable. Reports suggested intermittent clearing. As the aircraft ascended, conditions deteriorated. Fog advanced inland, reducing horizontal visibility. The runway environment, expected to appear within a defined distance, remained obscured. The crew continued the approach, anticipating late visual contact. Altitude reached minimums. At this point, procedure required either visual confirmation or execution of a missed approach. There was a delay, measured in seconds, possibly influenced by expectation, an assumption that visual reference would emerge momentarily. In many previous operations, it had. This time, it did not. Descent continued marginally below the prescribed altitude. The deviation was slight, but sufficient. Without visual cues, and without immediate recognition of altitude drift, the aircraft entered a zone where terrain and obstacles were no longer assured to be clear. Again, there was no automated warning. Recognition occurred as the aircraft passed below a safe threshold. The crew initiated recovery, but the delay, though brief, had removed the margin required to complete it. The aircraft impacted terrain short of the runway. The sequence was not abrupt. It was progressive. An expectation carried slightly too far, a decision extended beyond procedural limits, and a system that did not intervene. Case 3. System limitation and position uncertainty. The third event introduced a different variable. Position uncertainty. The aircraft was operating over a remote region, outside continuous radar coverage. Navigation relied on radio aids spaced at significant intervals. Between them, Position was inferred based on timing, heading, and wind correction. During the flight, a minor navigational discrepancy developed. Wind conditions differed from forecast. Ground speed varied slightly from expectation. These differences, individually insignificant, began to compound over distance. The aircraft's actual position diverged gradually from its assumed track. The deviation was not immediately apparent. Instrument indications remained consistent with expected progression. Without external reference, there was no direct confirmation of drift. As the aircraft approached descent phase, altitude planning was based on assumed position relative to terrain. That assumption was incorrect. The aircraft began descent earlier than appropriate for its true location. Terrain clearance, calculated for a different position, no longer applied. In the absence of radar monitoring, there was no external correction. Within the cockpit, awareness remained aligned with the original navigation solution. Descent continued. Terrain, once again, rose beneath the aircraft, this time not because of procedural deviation, but because of positional error. Recognition occurred only when visual or instrument cues indicated inconsistency. By then, altitude was insufficient. Recovery was attempted, but, as in previous cases, the margin had already been lost. Convergence of events. These accidents differed in detail. One involved descent beyond profile. Another, delayed decision-making under deteriorating visibility. The third, navigational drift in a system without continuous positional verification. Yet the outcomes aligned. In each case, the aircraft remained operational. The crew acted within a framework of expectation. Environmental conditions reduced clarity. Systems did not provide timely intervention. The failures were not independent. They were interconnected. A lack of terrain awareness systems allowed descent below safe altitude to continue without alert. Procedural navigation, without continuous validation, permitted position uncertainty to persist. Human factors, expectation, workload, assumption, extended decisions slightly beyond safe limits. None of these elements alone caused the accident. Together, they formed a chain. And once that chain was understood, not in isolation, but across multiple investigations, it became clear that the system required more than incremental adjustment. It required structural change. The accidents did not end at the point of impact. In aviation, that moment marks the beginning of a different process, one that is slower, methodical, and deliberately unemotional. Wreckage is examined. Data is reconstructed. Timelines are rebuilt from fragments of evidence that, individually, reveal little, but collectively define the sequence with precision. In Australia, these investigations were conducted under increasing levels of technical rigor. Early inquiries relied on physical evidence, pilot records, maintenance documentation, and, where available, radio communication transcripts. As technology advanced, flight data recorders and cockpit voice recorders began to provide a more detailed reconstruction of events, capturing not only what the aircraft did, but how the crew responded in real time. The objective was not attribution. It was understanding, reconstructing the chain. Across multiple investigations, a consistent pattern emerged. No single failure explained the outcome. Instead, each accident revealed a sequence, small deviations, environmental constraints, and system limitations aligning within a narrow window. Investigators began to move away from isolated causes and toward error chains, a structured understanding that accidents occur when multiple defenses fail simultaneously. In cases of controlled flight into terrain, the findings were particularly clear. Aircraft descended below safe altitude without awareness of proximity to the ground. Crews believed they were operating within acceptable parameters. Procedures, as written, had been followed, until a point where interpretation or execution diverged slightly. The absence of onboard terrain awareness systems was identified as a critical gap. Without such systems, there was no independent mechanism to alert crews when altitude became unsafe relative to terrain. The aircraft, regardless of sophistication, could not assess its own proximity to the ground beyond basic altitude readings. This limitation was not unique to Australia, but within its operating environment, where visual cues were often unreliable, it carried heightened significance. Human factors formalized understanding. Investigations also began to address human performance with greater precision. Earlier reports often referenced pilot error as a generalized conclusion. Over time, this language evolved. Investigators recognized that such descriptions lacked explanatory value. They did not account for why the error occurred or how it could be prevented. A more structured approach emerged. Decision-making under uncertainty was examined. The role of expectation, particularly during approaches where visual contact was anticipated, was analyzed in detail. Delays in executing misapproaches, even by seconds, were understood not as negligence, but as predictable human responses within certain operational contexts. This shift led to the formal adoption of crew resource management, CRM, principles. Communication within the cockpit was redefined. Authority gradients were addressed. First officers were trained to challenge decisions when necessary, and captains were trained to encourage that input. Cross-verification became standard practice rather than optional behavior. The objective was redundancy, not in systems, but in human oversight. Technological response. Perhaps the most visible outcome of these investigations was the introduction and eventual mandate of new onboard systems. Ground Proximity Warning Systems, GPWS, were identified as a critical advancement. These systems monitored aircraft altitude, descent rate, and configuration, comparing them against known safe parameters. When a deviation occurred, particularly one indicating potential terrain conflict, the system generated an immediate auditory warning. Terrain, pull up. These alerts were designed to bypass interpretation. They were direct, and they were time-critical. Later developments, including enhanced GPWS, incorporated digital terrain databases, allowing aircraft to see the ground ahead, even in complete darkness or cloud cover. This transformed situational awareness from reactive to predictive. In parallel, navigation systems improved significantly. Inertial navigation systems reduced reliance on ground-based aids. Satellite-based positioning, introduced later, provided continuous and highly accurate location data, eliminating many of the uncertainties associated with procedural navigation. Air traffic control systems also expanded. Radar coverage increased beyond major urban centers, extending into previously unmonitored regions. Where radar remained impractical, alternative surveillance technologies were introduced, allowing controllers to maintain more consistent awareness of aircraft position and altitude. Communication infrastructure was upgraded. Gaps in radio coverage were reduced. Reporting intervals were shortened. The system became more responsive, more connected. Regulatory evolution. Oversight bodies, including successors to the Civil Aviation Authority, began implementing changes not only in response to specific accidents, but as part of a broader safety strategy. Regulations shifted from compliance-based models to risk-based frameworks. Operators were required to identify hazards proactively, assess operational risks, and implement mitigation strategies before incidents occurred. Safety management systems became standard, embedding continuous evaluation into daily operations. Training requirements were updated. Simulators were used to replicate scenarios that had previously only been encountered in real-world operations. Low visibility approaches, navigation failures, terrain proximity events. Crews were exposed to conditions that demanded rapid recognition and response, reinforcing both technical skill and decision-making under pressure. Importantly, reporting culture changed. Incidents that did not result in accidents were no longer dismissed. They were analyzed, documented, and used to identify emerging risks. The system began to learn not only from failure, but from near failure. Industry-wide impact. Major operators, including Qantas, integrated these changes into their operational frameworks, often exceeding minimum regulatory requirements. Standard operating procedures were revised. Checklists expanded. Training cycles incorporated recurrent evaluation of both technical and human factors. Regional carriers followed, supported by regulatory oversight and industry guidance. The transformation was not immediate. It occurred incrementally, each recommendation implemented, evaluated, and refined. But over time, the cumulative effect became measurable. Accident rates declined, particularly in categories that had previously been recurrent, such as control flight into terrain. This was not the result of a single innovation. It was the outcome of alignment, technology, training, procedure, and oversight reinforcing one another. A system redefined. By the late 20th century, the Australian aviation system had undergone a fundamental shift. Where once safety depended heavily on procedural precision and human interpretation, it now incorporated layers of automated monitoring, predictive warning, and structured human collaboration. The margin, once narrow and easily consumed, had been expanded, not eliminated, but reinforced, and that reinforcement was built directly on the lessons extracted from the accidents that preceded it. Each investigation contributed. Each finding adjusted the system. Each change reduced the likelihood that the same sequence would occur again. The changes did not arrive all at once. They accumulated quietly, deliberately, layer by layer, until the system that once relied heavily on human precision alone became something more resilient. Not immune to error, but structured to anticipate it. Modern aviation in Australia operates within that structure. An aircraft departing from Sydney or Melbourne now does so within a network that extends far beyond the visible. Its position is continuously tracked, not inferred. Its altitude is monitored not only by the crew, but by onboard systems capable of detecting unsafe proximity to terrain in real time. Where earlier crews constructed their awareness from limited inputs, modern crews are supported by layered information, navigation displays, terrain mapping, predictive alerts. If descent begins too early, the system recognizes it. If terrain rises unseen, the aircraft is aware of it. The warning is immediate, and it does not depend on interpretation. This transformation is not defined by technology alone. It is procedural. Crew resource management is no longer an emerging concept. It is embedded. Communication within the cockpit is structured, deliberate, and expected. Assumptions are challenged. Decisions are verified. Redundancy exists not only in machines, but in human interaction. Training reflects this shift. Scenarios that once occurred without precedent and now rehearsed repeatedly. Low visibility approaches, navigation discrepancies, terrain conflicts. Each is simulated, analyzed, and internalized. Crews are not expected to rely solely on experience. They are prepared through repetition. The environment, however, has not changed. Australia remains vast. Remote regions still offer few visual references. Weather continues to shift, sometimes rapidly, sometimes without clear indication. The terrain, in many areas, still rises without dramatic definition. What has changed is the system's ability to manage that environment. Air traffic control coverage extends across areas that were once unmonitored. Surveillance technologies provide continuous updates. Communication gaps have narrowed. Where procedural control once operated in isolation, it is now supplemented by real-time data. Regulatory oversight has evolved into a continuous process. Safety is no longer assessed only after failure. It is monitored during routine operation. Data is collected, analyzed, and used to identify emerging risks before they align into something more significant. The system adjusts incrementally, often without visible disruption. This is the legacy of those earlier accidents, not as isolated events, but as catalysts. Each one contributed to a deeper understanding of how aviation systems behave under strain. Each one revealed a limitation that could be addressed, not perfectly, but effectively. Over time, those adjustments formed a framework in which the same sequences became less likely to recur. The absence of recurrence is not accidental. It is designed, yet the foundation remains unchanged. Aircraft still descend through cloud layers where the horizon disappears. Crews still rely on instruments when external reference is lost. Decisions are still made under conditions of uncertainty, where timing and interpretation remain critical. Safety, even now, is not absolute. It is maintained through vigilance, through adherence to procedures that were written, in part, from the outcomes of past events. There is no visible marker for this progression. Passengers do not see the systems that monitor terrain beneath them. They do not hear the simulated warnings practiced in training environments, or the data continuously evaluated by safety departments. The flight appears routine. And that is the point. Modern aviation safety is most effective when it is invisible, when the margins are preserved without intervention, when the conditions that once led to accident sequences are intercepted long before they develop. In Australia, that invisibility was earned, not through assumption, but through analysis, not through a single event, but through many, each one examined, each one understood, each one contributing to a system that now carries forward, not the memory of the accident itself, but the lessons extracted from it. The aircraft continues its descent. This time, the terrain below is not unknown. The system is away. The margin remains intact. And the outcome, unlike before, is uneventful, quiet, as it was always meant to be.